Hello everyone. In this section, I will talk about how to design Arbiter. So these are the contents for this section. I will first explain the function of Arbiter. Then I will talk about the two common implementations of Arbiter. The first one is fixed priority arbiter. Then the next one is so-called round robin, but I call it as pseudo round robin. Then I will talk about how to design a real round robin arbiter. Then I will try to extend the algorithm or the hardware architecture to support of any arbitration algorithm. Okay. So let's see what's the function of arbiter. Arbiter is used only when you have this situation, when multiple requests need to access a single resource. So in this situation, you need a block to route only one request to the destination resource at a time. For example, if we have 4 modules, A, B, C, D, they all want to access, you can say they all want to read and write the same resource, the single port SRAM. So as you have known, there is just a port, yes, a port and the SRAM micro, so it can't be connected to 4 ports here. Yeah, as we have talked about, so the situation here is the SRAM here, it has this input port and this output port, but for these wires, it means this wires already has all the ports here. That is, you have the C underline 0 or C underline A, there is C underline B, and there is also ADDR underline B, ADDR underline C. So this single line represents all the signals here. So you can't just add them together or all them together, or even you can't multi-drive. Okay, so you have to do something. So you have to add something between the source and the destination to enable just one request will access the destination at a time. So when you make some system like that, you have to change to the architecture in the right hand. You have add the module between them. So this is the arbiter module that will do arbitration. For any cycle, it will just select only one request and route the request information to the destination. For this case, it will route the chip select, write enable, write data, and the write address to the port, of single port SRAM. So this is the general function for an arbiter. Okay, if you just consider the request and the ground signal, so and we omit other information along with the request. For the SRAM access example, the other information is the write enable, write address, and write data, and something like that. So the block diagram of the arbiter can be simplified to something like that. Yeah, you have clock reset and the request, and you have the ground. The ground is feedback. Yes, is feedback to the request to tell the source that your request has been granted. For the SRAM case, this signal maybe the chip select, yes, chip select from module A, chip select from module B, chip select from module C. Okay. So as we have said, for a single time, there is only one request is allowed to route to the destination. So you can infer that these ground signals, they must be 1 hot. Yes, they must be 1 hot signal. That is, for any cycle, there is only one and just one will be active. All the others will be inactive. And it's also okay for all of these signals are in active state if there is a low request at some time. Okay, if you have generated the ground signal, so routing of the other information will be simple. Yes, you can just use the marks to select the other information along with the request and route to the destination. Such as the SRAM case, you can use the 1 hot decoder. Yes, you can use these signals and the select and use the 1 hot decoder to select the write-enable address, write data along with the request. Then after the marks, you can collect the marked signal to the ports of SRAM. Yeah. Okay, one more question for you. How to collect the D out? Yes, how to route the signal of D out from SRAM, the output of SRAM, D out. How to route this signal to the source block. You can say to the request block. If you want to design an arbiter, you can write the IO define as below. This is a block diagram I have talked before. Then you can define the IO signals, write a document like that. So the request and ground signal, as I have explained, they are something like the handshake interface. Yes, the valid ACK handshake interface. Yes, they are something like that. Or you can say almost they are the same. Okay, let's say the protocol and waveform for Arbiter. Okay, I have said this before. So actually the request ground pair is a handshake interface. So these are something the same as the handshake interface. For request, you can be active at any cycle if you want to request something, and you can keep at the request state after ground if you want to access the destination again. And the request must be honest. That is, once you assert request must be kept at high until there is a ground. Then you can go to inactive state. You must be honest. So for this case, if the request is dropped at this point, this is illegal. And for ground, okay, for ground, there is always no restriction on ground. Ground can check the status of request, then assert ground. You can pending, such as you can pending ground. Yes, you can pending ground to one request source, such as we can pending ground to request 0. Then at this cycle, at this cycle the request 0 has get the access. Yes. Okay. So this protocol is the same as the protocol and handshake. But you need to notice that ground, the output of grounds must be 1 hot. There is only one pending output at any time. For example, if in this cycle you pending ground to request 0, so the ground 1 to ground 3 must be 0 at this cycle. Okay, let's first study some UU arbitration algorithm. The first one is fixed priority. What is fixed priority? It means the priority of each request is fixed at the design. You can define the priority of the full request from high to low. Then we can define request 0 has the highest priority, then a little lower. This is the lowest priority. So when request 0 goes too high, it always gets granted. And if request 0 is high, it will block all the requests after it. So the circuit to implement this algorithm is something like that. You just use the cascade mux. Or you can say in real code is something like if else, yes. This is the highest priority. This is the lowest priority. When request 0 is high, you always max the ID of 0 to the output. So you can generate the ground 0 output. Yes, this is a binary encoding of ground. You can decode it to the 1 hot encoding. Yes. To binary, you can decode it to 4 1 hot signals. Okay. And for this circuit, if there is no request, the output will be 3. So actually it's pending to request 3. Can you write a real code for this circuit? Yeah, this should be simple for you. Okay, this is the real code for this circuit. Very simple. Just if else, then actually in hardware there are the cascade of mux. Okay, let's give this circuit a symbol like that. Request ground ID. Okay, inside it is fixed priority algorithm. We will use this symbol in the later slides. Okay, let's go on with the next arbitration algorithm. Someone call it as round robin, but I call it as pseudo round robin. I will explain why it's pseudo. So what's the problem of fixed priority arbiter? Do you have some complaint about the fixed arbitration algorithm? For example, this is a cycle. And for many cycles, okay, this is 1. Okay, so if the request 0 want to redirect the SRAM for 100 cycles, so it will assert request for 100 cycles, and for the first of 100 cycles, the request 1, request 2, request 3 also want to access, but only request 1 get the access. Yes, there is no access for request 1 up to 3. Only request 0 is get granted. Then after 100 cycles, is request 0 gives 0 and request 1 will be granted. Yes, and request 1 want to access for 200 cycles. Then for the first 300 cycles, request 2 and request 3 will never get granted. So this is a problem. If there is high priority request, the lowest priority request will not be granted for a long time. They will be blocked for a long time. So for some systems, this may can't work. So if you want to solve this problem, the key point here is you must change the priority of each request on the fly. Yes. Can you figure out the algorithm and the circuit diagram that support the change of priority on the fly? Okay, you can think about it for several minutes. I will go on. So one common idea is you can use a register to identify which request has the highest priority at a time. So at this time, which one has the highest priority, and some cycle later, which one has the highest priority. And for the other requests, the priority will be ordered as their IDs. For example, if this is the register we use to record the highest priority for this time. When the value of this register equal to 0, that means request 0 has highest priority. So the priority is something like that. And when the value of this register current priority is 1, so request 1 has highest priority. Then request 2, request 3, and wrap back to request 0. And if the value of current priority is 2, so request 2 has highest, request 3 followed by, then wrap back to request 1 and followed by wrap back to request 0 and followed by request 1. So of course, if the current value is 3, I think you can write the priority for each of the requests. So this is the ideal. Yeah. So can you think about? Can you figure out the hardware circuit diagram for this algorithm? Or can you write the actual code for this algorithm? Okay, this is the block diagram given by me. Okay, this is a fixed priority arbiter we have used before. Okay, they are fixed. So how to implement this function? So in this figure, you can say you have 4 fixed priority, but the collection is different. For the first one, yeah, their the collection of each request is in the order as their name. But for the second one, the input signal here, request 0 is actually collected to this point. Okay. And request 1 here is actually collected to the signal of this signal. There are 1 bit shift. That is, I try to use this block to do arbitration of this priority order. Yes, request actually is request 1 has the highest, then followed by request 2, request 3, then right back to request 0. Yes, this signal connected to request 0. Yes. Okay. So for the last one. Okay, for the third one. Okay, for the third one, it will do arbitration for this priority, for this setting of priority. Yes. Request 0 actually connected to request 2. Yes, the highest priority. Okay. So we put 4 fixed priority arbiter here to do arbitration for the 4 different priority setting. Then each block will generate their output. Yes, we use these marks to trace back the ID of the actual request. For example, if this gives 0, the actual request is 0. Okay, if this gives 2, ground 2, this signal is grounded, so the actual request is 2. There is no problem. Okay, and for this one, if the output here is 0, that is request 0 is get grounded, and actually it's connected to request 2. So 0, it will select 2. Yes. And if this is 2, ground ID is 2, the output. So request 2 is get grounded, and request 2 is collected to request 0. Request 0. So 2, 0 will be marked to this point. Okay. So the 4 marks here is used to trace back the ID of the actual request for each of the fixed priority arbiter. Then we use the current priority register to select the right group of arbitration result. Yeah, that is, we select which priority setting we want. Yes, we want this setting or we want this setting. Yes, if the value here is equal to 2, then we will select this setting to the final output. Yes. Yeah, if it is equal to 2, we want the result of this part. Yes. And we have traced back the real request, the index of the real request by using the marks here. Then the index of the real request can be outputted at this point. Okay, please try to understand the architecture of this hardware circuit and the algorithm here. Try to match them. Okay, I think this should be a little hard for beginner, but you have to try to train your ability to match the hardware architecture and the algorithm. Okay, it's also hard for me. Okay. So based on the algorithm, the hardware architecture, can you write the actual code for this algorithm? Okay, I will give you the code for this algorithm. Okay, please read the code below for 1 minute or 2. Okay, just pause the video. Okay, I will go on. So this is the mux, the final mux. Yes, the case of the current priority. So this mux is a mux here. Okay. So within each block, in this block. So this block is actually the circuit here. Yes. Oh, sorry. This block is actually the circuit here. Yes. Okay, let me show you the code. Okay, let me show you the code along with the figure. Yes, this part. This part of the code is actually the diagram here. And this signal is used to generate the priority of next cycle. Yes. This is used to generate the priority of next cycle. So you can see the algorithm here is if the request 0 get granted. So at the next cycle, the ID after it will be the highest priority and 0 will be the lowest. Yes. ID change to 1 and 0 will be the lowest. And if this is also true for other requests, if request 2 is granted, so the next ID will be changed to 3. 3 has highest priority and 2 has lowest priority. So for the logic of current priority equal to 1, okay, this is the logic. Actually, this logic should be this block diagram here. Yes. The value of request 1. Yes, request 1 has the highest priority. And then how about for priority value equal to 3? This code is a function of the diagram here. Okay, so the algorithm here is we use one register to hold the highest priority, and how to adjust the priority. The request get the grant will have the lowest priority in next cycle, and the ID after the granted request will have the highest priority order. Okay, let's take a whole look of the actual code. Okay, the IO define. Then you define the priority and the priority for next cycle. Then we all the requests together to generate the arbitration time signal. So this when this signal is high, it means there is at least one request. Then we have said this part before. Yeah, this part is simple. Okay. So this part, you will decode the 1 hot ground. Yes, you decode the 1 hot ground using the ID we generate here. The ID we generate here to decode the 1 hot output of each ground. And we make sure the ground is just a 1 cycle pulse. Then, when there is arbitration, we will shift the, or you can say adjust the priority of each request. Yes, this is the request we calculated for next cycle. Yes. Then after arbitration, after each arbitration, we will update it to the current priority register. Okay, that's all. For the round robin algorithm, if you still occur this situation, request 1 assert request for 100 cycles. So all the requests will get granted within the 100 cycles. They will be granted with about equal opportunity. Maybe each one will get 25 grant in 100 cycles. If they all assert request in the 100 cycles. But is there any problem for the so-called round robin algorithm? Does it running round robin? So let's check the sequence here. This is time. Okay, the time of cycle. So this is the cycle 1, cycle 0, cycle 1, 2, 3, 4. Okay, so for cycle 0, the priority is the value of priority rate is 0. So request 0 has highest priority, but at this time, request 0 doesn't assert the request signal, and just the last 3 has asserted the request signal. So in this situation, this one will get granted yes. So in the actual code we have seen before, this one will, the request 1 will get granted at the next cycle. Yeah. So it will grant this one, and the priority rig will be shift. Yes, will be adjust to 2. Yes, if as we grant request 1, so request 2 will have the highest priority. Yes. So for 2, the priority for all the requests will be yes. Yes. So at this cycle, if request 0 assert the request, but the priority has changed. Yes, has changed. So request 0 can't get granted. The grant signal will be request 2. And after request 2 is granted, the priority rig will be changed to 3. Then the priority will be So 3 has the highest priority. So this cycle 3 will be, the request 3 will be granted. And last, at cycle 4, the request 0 is granted. So you can see the problem here. At the beginning, request 0 has the highest priority, but it just didn't assert its request. Then the priority of request 0 can drop to some lower priority. Yes, lower. Yes, and dropped to some lower priority. Yes, it will be granted sometimes some cycles later, not immediately. So this is the problem of the algorithm we have introduced before. Can we define the behavior of arbitration in that manner? The first is the priority of a request can be lowered only after it has been granted. And the second is the granted request will adjust to lowest priority, and all the requests with higher priority, and all the requests with lower priority than the granted request will increase their priority by one step. And the request with higher priority than the granted request will keep their priority order. So for example, there is 4 requests begin with request. This is the highest. This is the lowest. Okay. So after we grant request 1, assume request 0 equal to 0. So the priority of request 0 will keep, and the request with lower priority will shift one step to higher priority, and request 1 will change to the lowest. So if we grant request 1 again, so the priority of the higher part will keep, and request 1 will be the lowest. Okay, will be the lowest one. Then if we grant request 3, so all the requests higher than request 3 will keep, and the request lower than will increase one step. Request 3 will be the lowest. Then if we grant request 0, then all the requests lower than will be shift one step, and request 0 will be the lowest. So can we make something like that? How to make this behavior in hardware? What's the hardware architecture for this algorithm? Please think about it. Okay, let's take a break here. Please think about it for several days or several hours, of if you are smart, maybe several minutes. Okay. Thanks.